Hi and welcome to the lesson of multivariable calculus. So in today's class, we are going to discuss Green's theorem. That is very important topic of multivariable calculus. So, and in fact, it is the fundamental theorem of the line integrals. So previously we discussed about line integrals and we discussed a problem of work done along a path of this kind. And that was a helix, right? So to compute the work done over this helix, what we did was we know that the work done by a force field is F dot dr, where dr is the infinitesimally small arc length, and if we sum of all these arc lengths that is given by the integral along this curve, we get the total work done by the force field along this helical path, right? So we parameterize this curve in order to find the work done. And in most of the cases, it can be more complex. For instance, if we have a curve of this kind, let's say uh, we have a curve in this direction, and then we have a line in this direction, and then we have some curve like this, and then for instance we have a curve like this, right? So in these kind of situations where we have uh, multiple curves that forms a closed curve, the line to computing the line integral becomes more complex because we have to compute the integral over different paths, and then we have to add all of these, and then we need to parameterize all the paths along which we are going to compute the line integral. But Green's theorem makes it much easier to compute this line integral, because it says that if we have a vector field along this curve C, for instance, let us take an arbitrary simply closed curve. That is, the curve is closed without any self-intersection, and we can just give its orientation, for instance, in the counterclockwise direction, and let's call it curve C, and then we can see that it encloses a region inside, that is, we can call it region R. So now instead of computing the line integral over this curve C, or we can just assume that if we are calculating the work done by a force field on a particle along this curve C, so instead of computing that, if we compute the curl inside this region, then we can say that it is simply equal to this line integral over this curve, right? So this is what does actually this Green's theorem says. So we have a vector field here. We can see that it is represented by m dx plus n dy. So if we want to compute the line integral of this vector field over this curve, so we can simply compute the double integral of the curl inside this curve. So that is equals to the double integral of the curl dou n over dou x minus dou m over dou y bounded inside uh, the curve, that is the region. So what actually it is doing is that it is breaking this region into a smaller areas, and then uh, collecting all the areas to sum up and to give the total circulation in this region R, right? So this is what does it mean? So we can say that this is, for instance, a small region, that is this region. Let's say this is dA, and this is the partial derivative of the force field. That is the difference, which shows that this is the curl, that is del cross F, right? So now let us take some examples and see how it works. Now, for instance, let's say we have this problem, use Green's theorem. Forget about this, that use Green's theorem. And just we need to compute this integral. For instance, this is the line integral, that is x squared plus y cubed dx plus 3x y squared dy. And we need to find the line integral over the curve C, where C is the portion of this parabola y equals to x squared from 2 comma 4 to 0 comma 0, and followed by the line segments uh 0 0 to 2 comma 0, and from 2 comma 0 to 2 comma 4, which is just shown here, right? So this is the curve. You can see here, this is the curve y square, y equals x squared. This curve here, this is y equals x squared uh, from 2 comma 4 to 0 comma 0. So this is the origin, that is 0 comma 0. This is the point 2 comma 4. So 2 comma 4 to 0 comma 0 means it is oriented counterclockwise, that is this way. And then it is followed by the line segment 0 0 and 2 0. So 0 0 to 2 0, this point here, 2 comma 0, and then from 2 0 to 2 comma 4, that is this line here. So now if we want to compute the line integral, we have to add up all these line integrals. And before doing that, we need to parameterize the curve as well to find the limits and to make this function uh, easily integrable, right? But instead of doing that, if we consider the region that is bounded inside, that is this region R, so we can first of all find the curl of this region simply by dawa n over dawa x minus dawa m over dawa y. So m equals x squared plus y cubed. This is m and this is n. So this is the form of m dx plus n dy, and n equals 3x y squared. So m y equals 3y squared, nx equals 3y squared. So now the double integral over this region is going to be 3y squared minus 3y squared dA, which is 0, right? So now we can see that how easier it is to compute this and how faster. Instead of computing each curve, we just simply computed the partial derivatives, and we see that the curl along this closed region is 0. So the integral is 0. Therefore, the line integral along this curve is 0, right? So this is how it works. Let's take more example. For instance, now we can see here we have a circle. We have to evaluate this line integral over the circle. And again, we will use the Green's theorem instead of choosing the line integral. So m equals 7y minus e to the power sine x, and n equals 15x minus sine y cubed plus 8y. And my is going to be 7 and x is going to be 15. So the integral is going to be 15 minus 7 dA. Now the region is given, it is a circle. It is a circle, so we can see here that circle of radius 3. So radius, that is a 3, r equals 3. and centered at 5 comma minus 7. So the center is at 5 comma minus 7. So 15 minus 7, it is 8, and the integral over the region dA, this is nothing but the area of this circle. So we can say that 8 times pi r squared, where r is given as 3. So 8 times pi r squared, that is 3 squared, is 9. So multiplied by 9 is simply 72 pi. So the computation is now much easier by using the Green's theorem. Now one more example, we can see here that we need to find line integral, but we will use the Green's theorem. So m in this case is given as e to the power x plus 6xy n equals 8x squared plus sine y squared. So my is 6x and x is 16x. Therefore, the integral over the region, it becomes 16x minus 6x and dA. So it is 10x dA over the region R. Now we need to find the limits, that is the limit of this region. So on the okay, so it's a circular region. It's kind of we can say that a quarter circle, right? And if we extend this, you can see that this is a circle and this is also a circle. So the area bounded between these two circles is this whole area. But we are only interested in this region, that is the blue region, this blue region here, right? Because it is said that it is centered at the origin and lying in the first quadrant. So we are only interested in the first quadrant, right? This part. So we can simply say that we can take this 10 outside. We have x dA. So it is a circular region. We can use the polar coordinates. So x equals r cos theta, y equals r sine theta, which gives dA equals r dr d theta. So it becomes 10 integral over the region r dr d theta. But we have x, so we have to write r cos theta as well. So r cos theta dot r dr d theta. Now the limits of r are from 1 to 3, this region 1 to 3. So we have 10 multiplied by the integral over the area. So limits from 1 to 3, and the theta, it goes from 0 to pi over 2, right? So it goes from 0 to pi over 2 because it is going to the y-axis. So it's from 0 to pi over 2, and it's r squared cos theta dr d theta. Now we can easily compute this integral by first integrating with respect to r. So we get r cubed over 3 from 1 to 3 cosine theta d theta from 0 to pi over 2, and we have 10 outside, and when we solve it, we get this result, that is 260 over 3. So that is how we compute this problem using the Green's theorem. And if you are going to solve it using the line integral, then we have these 4 curves. So we need to compute each curve separately, and then we need to sum up all the curve to get the line integral over this simply closed curve. So this is how does the Green theorem work. So I hope you guys understand this. Thanks for watching the lesson. That's all for the time.